I'm going to introduce some facts about the Riemann zeta function. So the Riemann zeta function is defined to be this Dirichlet series for some complex variable s, and this series converges absolutely when the real part of s is strictly greater than 1. This function has an analytic continuation to all of C except for the point s equals 1, and at s equals 1 you have a simple pole and the residue is 1. So you can write the Laurent series of zeta of s at s equals 1 as 1 over s minus 1, and then it turns out that the constant term here is this gamma naught, which is the Euler-Mascheroni constant, and then you have a plus big O of s minus 1. So here I'll define the Euler-Mascheroni constant. Let me make sure I know how to spell it. And this constant is, one definition is to look at this partial sum of 1 over n. So if we have 1, 2, 3, 4, 5, and then we look at 1 over n, maybe we'll have 1, 1/2, 1/3, 1/4, etc. Okay, so we can think about this area here. This area is the sum, and this area is approximated by the integral of 1 over x. So that integral looks like this line. And so this difference here, right, if you sum up these areas sum to the Euler-Mascheroni constant. And it is about 0.577. It's widely expected to be irrational, but I don't believe that's actually known. Sometimes you'll see this denoted C naught instead of gamma naught, because this lowercase gamma, sometimes you're doing something where the letter gamma is already taken, and so it's clearer to use a C here. So this is the Laurent series expansion of the Riemann zeta function at 1, and it's handy to know. Another important thing about the Riemann zeta function is the functional equation. So the functional equation is gamma of s over 2 over pi to the power s over 2 times zeta of s is equal to gamma of 1 minus s over 2 pi to the 1 minus s over 2 zeta of 1 minus s. So it's a functional equation that goes between s and 1 minus s. What people will do is they will define this function uppercase lambda of s to be just this thing here called the completed zeta function. And then the functional equation, you can write it simply as lambda of s is lambda of 1 minus s. And it's a little more compact, and you'll see this sort of thing done for other L functions as well. This symmetry, s to 1 minus s, means that by and large the way this goes is over here you have this region of absolute convergence of the series definition, sum 1 over into the s n from 1 to infinity. And so over here you can understand the Riemann zeta function easily just through analysis of this series. And then this functional equation tells you what's going on over here. So because you understand it here, and because you have this easy functional equation, you can understand the Riemann zeta function easily over here. And then this space in the middle is called the critical strip. And this is very mysterious. People have no idea what's going on in the critical strip, essentially. And in particular, the line 1/2 is called the critical line. So the Riemann hypothesis this is the conjecture that all the quote-unquote non-trivial zeros, and I'll talk about that in a second, of the Riemann zeta function lie on the critical line. Let me maybe state it this way. All the zeros of the Riemann zeta function in the critical strip are on the critical line. So this is widely believed to be true. It would be pretty shocking if it were false. And there's tons of numerical evidence for it, but also people have no idea how to begin proving this, right? This one is wide open. And this is one of the 7 millennium problems. This is maybe arguably the single most important conjecture in all of mathematics. And what we can prove is that there are no zeros on this right edge. On the line real part of s is 1, there are no zeros, but we can't get into the critical strip at all. I mean, maybe there are like a few zero-free regions, but nothing of constant width. The first 2 zeros, sometimes you'll be looking at something and you'll see these numbers pop up. They're at 1/2 plus I times 14 point something, 1/2 plus I times 21 point something, and 1/2 plus I times 25 point something. So if you see these, 14, 21, 25, maybe that's a hint that whatever you're doing is actually involves the zeros of the Riemann zeta function. So these are, like I said, called the non-trivial zeros. So what are the trivial zeros? So if we look at the functional equation that I'm going to write it this way, zeta of s is pi to the s over 2 divided by pi to the 1 minus s over 2 times gamma of 1 minus s over 2 divided by gamma of s over 2 times zeta of 1 minus s. And this is just exactly the functional equation, just rearranged. And let's look at the region real part of s is strictly less than 0. And that's because real part of s greater than 1, we know because of the series definition we can do everything that way. And in the critical strip, we have no idea. So the remaining region to look at is when the real part of s is less than 0. So here, how can this thing be 0? Well, if the real part of s is less than 0, then this piece is non-zero, right? It's some series, and you can show that it doesn't vanish. This part is non-zero because it's non-zero. When the real part of s is less than 0, then 1 minus s is going to be at least 1, so this gamma function in the numerator doesn't vanish. And then in the denominator, you can have some poles, right? So gamma of s over 2, this thing has poles when s is minus 2n. Well, I'm not going to count 0 because we're looking strictly less than 0. So this is going to be for n, 1, 2, etc. And what that means is that our Riemann zeta function is going to vanish at the negative even integers. And these are what people call the trivial zeros of the Riemann zeta function. And the Riemann zeta function doesn't vanish outside of these. And the only non-trivial zeros we know, in fact, they're strictly contained between 0 and 1. They're not on the edge of the critical strip. What happens at the point 0, because you might think, oh, well, the gamma function also vanishes at, or also has a pole at 0, so why doesn't this vanish there? So at 0, what you get is zeta of 0 is pi to the 0 over 2 over pi to the 1 minus 0 over 2, gamma of 1 minus 0 over 2, gamma of, okay, forgive me for writing it this way, and then zeta of 1 minus 0. All right. Obviously there's a, you know what I mean. So what's going on here? Well, this gamma, so this pi doesn't appear. This is a square root pi. Gamma of 1/2 is square root pi. So in fact, these two things cancel out. And here you have a simple pole with residue 1, and here you have a pole with, well, the gamma function has residue 1, but here you have a 1/2, so you actually get the value minus 1/2 at 0. And maybe you've seen elsewhere people write 1 plus 1 plus 1 plus dot 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 equals minus 1/2. And this is where that comes from, that if you analytically continue the Riemann zeta function, that analytic continuation has value minus 1/2 at 0. The series definition is not valid at 0, so I mean this statement is kind of nonsense, but it's a fun way to put it. Similarly, you'll see people write this 1 plus 2 plus 3 plus dot 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 equals minus 1 over 12. And that comes from the fact that zeta of minus 1 is minus 1 over 12. Again, pretending that you can use the series definition when you're not in the region of absolute convergence. You can't actually do that, but this is kind of fun, you know? Let's talk about the value at the negative odd integers. So zeta of minus 2n minus 1 is going to be, let me look this up. So it's going to be let me write it this way. Let me write the zeta function at minus n is equal to minus 1 to the n times the n plus 1th Bernoulli number, which I will define in a second, divided by n plus 1. So here, b sub n is the Bernoulli number, and the way to, and this formula is with the convention that b1 is minus 1/2. There are two conventions for the Bernoulli numbers, and the only difference between the two conventions is if this is half or minus 1/2. So, I mean, as we said up here, taking the convention, it's minus 1/2. So what are the Bernoulli numbers? Well, the way I would introduce them is through what's called Faulhaber's formula. I'm not totally sure how to pronounce this. But this is something that is maybe familiar, that if you look at the sum n from 1 to x of n to the k for k a positive integer, then there is a formula for this called the Faulhaber's formula in terms of the Bernoulli numbers. So this is equal to 1 over k plus 1 times the sum. Let me say j from 0 to k of k plus 1, choose j, and then you have this Bernoulli number times your upper bound for your sum, x to the k minus j plus 1. And this is an indirect definition of the Bernoulli numbers. The actual direct definitions, I mean, they're kind of convoluted, and this is where they come from historically, and this is the, I think, convenient way to think about them. So, for example, if you know the sum of consecutive squares or consecutive cubes, you can figure out the first few Bernoulli numbers. You might wonder how quickly these grow, because this is not totally obvious, and you can actually use analysis of the Riemann zeta function for that. So you know that the absolute value of, well, in fact, just the limit as s goes to infinity of zeta of s is 1, right? Because if you just think about the series definition, right, this goes to 1 because you always have this term 1 over 1, and then all the higher terms, they end up vanishing, right? So this fact combined with the functional equation, this implies that, what is the bound you end up getting? That the absolute value of the Bernoulli number, the 2nth Bernoulli number, is asymptotically 2 times 2n factorial over 2 pi to the 2n. Okay. And in particular, these eventually get quite big, right? So this is misleading. The first few Bernoulli numbers are pretty small. Let me make sure I look them up. Right, so the Bernoulli numbers start they go. So the even ones vanish after 1. So the Bernoulli number B3, B5, B7, etc. Those are all 0, but B1 is not 0. And so the values of the Bernoulli numbers at the even integers after 0. So B0 is 1, and then you get 1/6 minus 1/30, 1 over 42, and you might think that these are going to 0, and then minus 1 over 30, and then you have a 5 over 66, and you have a minus 691 over 2730, dot, dot, dot. And by the time you get to 20, for example, this thing is up to about 529. So they start off small, but don't let that fool you. These are going to infinity. The last thing I want to talk about for the Riemann zeta function is that the Riemann zeta function has an Euler product. So you can write the Riemann zeta function as the product over primes. And each factor is 1 minus p to the minus s to the minus 1. And proving this is quite easy. You just write this as, you recognize this as a geometric series, so it's a product over primes of 1 plus p to the minus s plus p to the minus 2s plus p to the minus 3s plus dot dot dot, right? Because if you had this expression, you would say, oh, that's a geometric series, it's equal to this, right? Right. Maybe it's slightly clearer if I just rewrite this as 1 over 1 minus p to the s. And then if you think about multiplying this out, so you take n and any integer n, and that integer n will have some factorization, p1 to the r1 times p2 to the r2 dot 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 times pk to the rk. And then in each factor, you go and you find the appropriate term, right? So you go to the p1 in this product, and then you take the the term where the r plus 1th term, right? The term where the exponent is r. And if you pick that, the appropriate factor, or the appropriate term in each factor, then those will multiply out to give you n. And this is a bijection, right? You get each n exactly once, so that tells you that this is in fact the series 1 over n to the s, n from 1 to infinity. So it's totally elementary, that has this an Euler product, but this Euler product is extremely useful for doing things. And so the three main things that the Riemann zeta function has: one, you have analytic continuation. Two, you have an Euler product. And three, you have a functional equation. And this is a pretty good template for L functions as a whole. Right? Anytime you encounter an L function, often you're going to want to figure out what these three things are for that L function. You're going to want to show that has an analytic continuation, you want to show that has an Euler product, and you want to show that has a functional equation. And that can be very difficult. But that's sort of the game that people usually play, and it's pretty universal. And sometimes, I don't know, sometimes you'll have things that look like they should have all of these, but then maybe surprisingly they don't, and that can be cool too.